So in phase one, what we try to do is that we try to plot the time response of the ECG signal on Scilab. So we have our coding here, and we plot the both plots in the same page, and therefore the code subplot. And we have also identified a couple of keywords, which is plot and plot 2D3. So for plot, basically it returns the continuous time signal of ECG signal, and plot 2D3 will return the discrete time signal of the ECG signal.
Next, ASCII format is one of the Scilab functions we study in Phase 1. The function shown on the slide is user-defined function with 6 input arguments, which are typed of ASCII format, figure numbers, lower and higher S and Y limits. These are the important syntax in ASCII formats used to map ASCII tab to fit exactly with accurate labelings. This is the full program for ASCII format function, which is able to do ASCII format for continuous time signal, discrete time, Z-plan, magnitude, and phase pattern. The coding across a red box will fit the ASCII to its default range if S and Y limits are inserted with 0 values.
In filtering, we came up with one function for each FIR and also IRR filters. For FIR filter, we are using WFIR functions. For IRR filter, we are using IRR functions. Below are the explanation for the syntax. Next, by using this code, we can see how the filters look like. And this one is for the IRR. Since WFIR and also IRR only used to generate the filters, so we need to use another code which is filter to filter out the noise. So on the right hand side is the results of the filtering.
For post-zero analysis, we can construct a Z-plane of FIR and IR filter using PLZR command where linear system function as its input argument. This is the example of constructing Z-plane of FIR filter. Next, these are the syntax to convert zero pole gain to transfer function and vice versa.
To perform frequency domain plot, the first thing we need to do is convert the time domain signal into frequency domain signal using the FFT function. And then we need to convert the frequency domain signal into magnitude spectrum using the ABS function. And lastly, using the plot function, we can plot the frequency domain plot. And this is the SciStep code that I run. And finally, this is the resulting frequency domain plot.
In filtering process, continuous time signal need to be sampled first by undergoing sampling process in the first part. For sampling, corrupt ECG.map file is assumed to be a sampled version of corrupt ECG signal and output of analog to digital converter. From the figure, we plot continuous signal by using plot command, discrete signal and discrete signal from frequency of 600 until 900 by using plot to discrete command. This discrete signal will be used to convolve with impulse response of FIR filter.
Convolution is the last part of the process. In order to obtain the output Yn, we need to convolve Xn with the Hn. Below are the codes we use for the convolutions. By comparing the figure 2 with the figure 1, which figure 2 is the output, we can clearly see that the output has less noise and the signal is better.
In FIR filter design, we use Z transform to plot the value of Hn on a Z plane. So this is a coding that we use in order to define the function Z plane. And in order to call the function, we will have to first create an array of 0, which has the same size as Hn, and we'll later use it as the pole. And next, we'll figure out how to flip Hn. And finally, we'll find the values of zeros, and then we transpose them in order to suit the function that Z-plane that we have defined earlier. And finally, we call the function, and this is the result that we get.
To perform discrete time Fourier transform, first create an array that contains e to the power of negative j omega n, then multiply discrete time signal Hn with the array, and finally using ABS to get the magnitude spectrum and phase mag to get the phase spectrum. As you can see, this is the example code that I run in SciStep. From the magnitude spectrum, we can see that this is a low-pass filter and everything after pi is a mirror image.
Windowing method is used to design FIR filter for EGC signal. Since noise is at high frequency, therefore low-pass filter with high cutoff frequency 100 Hz is our aim, and Hamming window is used to have stop band attenuation greater than 50 dB. This slide shows the impulse response and magnitude spectrum, which is obviously a low-pass filter generated by Scilab program on the left.